Good morning. Today we are going to continue looking at the matrix stiffness method and the specific problem. Till now we've been looking at a member that is essentially subjected to flexure, because we have neglected both the shear and the axial deformations in the member. Today I'm going to take up an example in which you will have a member which is essentially subjected to only axial forces, and we cannot neglect the effect of axial deformations. So what do we do in such a situation? So today again we're looking at matrix stiffness method application with respect by taking examples. Okay, so let me show you the problem statement and then we will see how to tackle it. Okay, so now this is the problem that we are looking at. Okay, what you have is a frame, and this is more in terms of a braced frame. This is a bracing. Now bracings typically are pinned at two ends, because essentially if you look at what happens to bracings in a frame are essentially to stiffen the frame and to take axial forces only. Bracing members are not normally designed for flexure. Okay, so this is a braced frame, a typical braced frame, and let's look at the typical loading that you would have. You would have this kind of a loading and this kind of a loading. Let me give some numbers. This would be EI, this would be EI, this would be EI. These are all framed members. Okay, note that this pin is only the connection of this brace. Okay, so it is pinned at both ends. So essentially this is only subjected to axial, and so the only definition that we have to do is to define its axial rigidity. Okay, and let me define some. This could be 4 meters, this could be 4 meters, this could be 4 meters. Okay, and this could be like 100 kilonewtons, and this could be 50 kilonewtons, and let me say that EI is equal to 1 into 10 to the power of 5 kilonewton meter squared, and EA is equal to 1 into 10 to the power of 8 kilonewton. Okay, these are just numbers that I am fitting in to ensure that you get explain what this is. Okay, so here in a sense, and let me put A, B, C, D. So here, if you look at it, you have essentially, if we look back, we have to look at the members. Okay, now AB is a member defined in this way, and its K AB is defined by 2EI upon L 2 1 1 2. Its V is, and this is A and this is B, so V is going to be theta AB, theta BA, and S are going to be MAB, MBA. Okay, so and SI0, since there is no loading, is going to be 0 0. Okay, so this is our definition of member AB. Similarly, by the way, let's go back here. How many degrees of freedom does this structure actually have? Essential. In other words, there is a degree of freedom which is theta d, but since moment at that point is equal to 0, this is essentially a 3 degree of freedom structure, which are 1 R1, 2 R2, 3 R3. So this is member AB, and similarly member BC is going to be, it's continuous over both B and C, and therefore what we have over here is V is equal to theta BC, theta CB. Okay, S is equal to MBC, MCB. SI0 is equal to, now here there is a loading, and the loading is 100 kilonewtons per meter. Okay, and so this is going to be PL upon 8. So PL upon 8 is going to be plus 50 minus 50, and KBC is going to be 2EI 2 1 1 2. So much for member BC. Okay, now for member CD. Now this member is continuous over C but pinned at D, and therefore its V is equal to theta CD, its S is equal to MCD, its SI0 is 0, and its KCD is 3EI upon L. That is for member CD. Now we have another additional member, BD. What kind of a member is it? It is actually, if you look at it, a member of this type, pinned at both ends, and it is only subjected to delta AB. So its V is equal to the axial deformation, its S is equal to PAB, its SI0, since there is no axial force in the member, is going to be 0, and K, this is B, this is D, so this is delta BD, delta BD, delta BD. Please excuse the error. And K of BD essentially relates this and this, and you already know that since delta BD is equal to BD into L upon EA, so the KBD, which is PBD in terms of delta BD, is going to be equal to EA upon L. L here in this particular case is 4 root 2. Okay. So this is an axial member. Okay? In fact, let me just point out, so this is something that we had not discussed and I'm introducing today. But the concept is the same. Whether it's a flexural member, whether it's an axial member, the only thing that happens is the member degree of freedom for flexure is the rotations from the chord at the two ends, whereas for axially loaded member, it is actually equal to delta, which is the axial deformation, and the load is the axial force in the member. Okay, and this is how. In fact, I'll just expand this. This, of course, is only a member which is subjected to axial. You might have a situation where you have a member which is subjected to both axial and flexure. How do we consider that? And so I'm going to divert a little bit, come back to this problem a little bit later, and treat how we may have a problem where we have a member and I'm going back to the basics, starting from flexibility and then going off from there. Okay, because you can always invert the flexibility matrix and get the stiffness matrix for a member. Okay, I've already shown that many times. Okay, so let's go back to this. And here, what we have is, we have MAB, MBA, and PAB. Okay, so this is a situation, so therefore here the flexural rigidity is EI and the axial rigidity is EA. Okay, now this is a situation where we are considering both axial deformations as well as flexural deformations in a member. This typically has to be done, although we tend to neglect it in a general situation. But suppose we want to consider it. How do we write down the V? Okay, if you look at it, the V in this particular case are equal to theta AB, I'm just saying A, B, theta BA, and delta AB. Delta AB is here, this. Okay, the deformation, the change of length of member AB actually. Okay, so this is different from the earlier situation. Now S is equal to MAB, MBA, and PAB. Okay, and if S is equal to kV, flexibility. This is what we find out by actually going through the process. And if you look at this, you will see that if I give a force P, you are not going to generate any bending moment. And therefore, you will see that theta AB and theta BA are equal to 0 if P MAB and MBA are equal to 0. And putting that in, we can see actually that V is equal to L upon 3EI, L upon minus L, 0 minus L upon 6EI, L upon 3EI, 0, 0, 0, L upon EA into M, A, B, M, B, A, and P, A, B. This is relatively easy to prove because V is nothing but equal to and for a straight member, PAB does not give rise to theta AB and theta BA, and MAB and MBA do not give rise to any delta. That is the reason why these are zeros. Okay? And therefore delta AB is equal to PL upon EA. We already know that. Okay, and these we've already evaluated earlier. So this is all that happens. If you have a member where both flexure and axial deformations have to be included, then all you have is this term, but you will see that in a straight member, these two terms are 0. So this actually, the axial deformations are uncoupled from the flexural deformations. Okay, but this in a sense is what happens, what becomes, and then of course you have to find out SI0, which are essentially fixed end moment at AB, fixed end moment at BA, and fixed end axial force in AB. In other words, if, for example, remember I talked about temperature, right? And if you have temperature, if you have the neutral axis expanding, then you actually have developed a fixed end force which you can compute easily. Okay, so this in a sense is the overall, but by and large, we do not, since these are uncoupled, we do not consider flexure and axial together, and that is the reason why, if I go back to the problem that I was looking at, I have one member which is an axial member, and therefore the axial member only has axial force, and this is E upon L. Okay. Now, so we've written down, so we have 4 members, 3 degrees of freedom. We've written down all the relationships for all the members. So what's the next step? The next step is kinematic relationships. So finding out, take every degree of freedom displacement equal to 1, and then find out what the member deformations are under that particular loading. Okay. So let us look at and I'm going to give it R1 equal to 1. So what's going to happen? And theta R2 and R3 have to be equal to 0. So this will also come here. Okay. So as far as, now let me draw it in a different pen. Note that these members are actually rigid, so they cannot deform. But this member can deform, and it does deform in fact. The only way it can go is this way. And so if I look at okay, so this is how it goes. So we have here this. Oh, by the way, this one doesn't go this way. This one goes this way because here you have 0. Okay, so we have this. So this is my theta. So this is going to be 1 by 4. Again, this is going to be 1 over 4. This is going to be 1 over 4. Okay. Now, the other thing that we have to find out is how much has this member shortened by. So to find out how much it has shortened by, we need to draw the perpendicular. Because note that whatever it has moved perpendicular by, that does not change length. So when we drop a perpendicular here, this is the amount of change of length. Okay? So this is 45 degrees. This is 1. So this is going to be 1 over root 2. Cosine of, this is 90 degrees. So this is cosine, sine of 45 degrees. Sine of 45 degrees is 1 upon root 2. Okay, that is the most important thing. And then, of course, we have theta 2 and theta 3 equal to 0. So we can plug that in. And those are relatively easier. If you give theta, you get this, you get this. That is for R2 equal to 1. Okay. Note that this point goes nowhere, and therefore this does not change length. Okay. The only thing that you have is this is equal to 1 and this is equal to 1. And when you put R3 equal to 1, all you get is this. This member remains the same. And therefore, if we were to write down our A's, so A, B is equal to corresponding to the first degree of freedom, this is 1 by 4, 1 by 4. Corresponding to the second degree of freedom, this is 0, 1. Corresponding to the third degree of freedom, this is 0, 0. If we look at A, B, C, corresponding to the first degree of freedom, it's 0, 0. Corresponding to the second degree of freedom, it's 0, 1, 0. And corresponding to the third degree of freedom, it's 1, 1. Then we have A, C, D. Corresponding to the first degree of freedom, it is from the chord to the tangent is 1/4. Second one, 0. Third one, 1. And ABD. What is ABD? This is the axial shortening or lengthening due to the unit displacement. And if you look at it, that in this particular case, what you have is you have a shortening due to R1, and shortening is defined as minus, so you have minus 1 over root 2. And what are the shortening in these two? 0, 0. Okay, so you see essentially the overall concept, whether you have an axial member or whether you have a flexural member or whether you have a member which has both flexure and axial, all that happens is that you have to consider both the effects together. Okay, so that's why this particular case, since BD is only an axial member, this corresponds to the axial deformation in member BD due to R1 equal to 1, due to R2 equal to 1, due to R3 equal to 1. Okay, so in a sense, there is no difference in the entire scheme of things, whether it is an axial member or whether it is a flexural member. Okay, so let us go through some of the numbers. I am not going to be solving this entire problem because all I wanted to introduce was the concept of this. Okay, so here ultimately what we have is we have SI is equal to KI AI into R plus SI 0. Okay, so in that way we can find out for each member, and for the flexural members AB, BC and CD, I am not, well, I can do it. Why don't we do it? Okay, let me do it for AB. For AB, what we have is KI is equal to 2EI 4 2 1 1 2, and my AI is equal to 1 by 4 1 by 4 0 1 0 0. So this becomes, so this implies that K into A is equal to, I'm going to keep the outside as EI upon 2, and the inside then becomes 2 by 4 plus 1 by 4 is 3 by 4, this way 3 by 4, this way 1, this way 2, and this way 0 and 0. Okay, similarly we can do it for BC. For BC, we have 2EI by 4 2 1 1 2 into ABC, which is 0 0 1 0 0 1. So this implies that KA is equal to EI upon 2. The first one is 0 0, the second one is 2 1, the third one is 1 2. Okay, so this is KA for BC, this is KA, and let us write it down for CD. For CD, KI is equal to 3EI by 4, and CD is 1 by 4 0 1. So this basically becomes then 3EI by 16 0 3EI upon 4. So that is for CD. This is Ka for CD, and for BD this is equal to Ea upon 4 root 2 multiplied by minus 1 over root 2, 0 and 0. So this implies Ka. Note that whether it is a flexural member or whether it is a actual member, the concept is still the same. Only thing is here we have Ea. So if I look at it, this becomes minus Ea upon 8, 0, 0. Okay? And we know the values of Ei and Ea, so we can plug those in. Okay? So now, once we have that, then ultimately we have this. R prime is equal to summation Ai transpose Ki Ai summed over all the members into R plus summed over all the members of Ai transpose Si 0 plus summed up over all the members Ni 0. Okay? So if we do this, okay, so let's first find out this. This one we know only exists for BC. This only exists for BC. It's 0 for all the others. Okay? And the major thing is that if you look at it, the NIO are the reactions, and we can show, again, if we look back at the shape, okay, corresponding to this, there is no vertical displacement of these points, and in R2 and R3 there are no vertical displacements. So in this particular case we can see that this is going to show up as a 0 vector. Okay, this does not exist, and this will only show up for BC. So let us do this first for BC. So for BC, which is the only one, Ai transpose Si 0 is going to be equal to, Ai transpose would be 0, 0, 1, 0, 0, 1, and Si 0 we've already seen was equal to 50 minus 50. And so if we look at that, this becomes equal to 0, 50 minus 50. Now, if we look at the R, and we find out the work done by the nodal forces, we will see that in this particular case this becomes 50 and these don't do any work. And so therefore what we have is, and now next we have to find out the Ai transpose into Ki Ai for each member. Okay, and that one I'll first do it for the members which are the smaller ones, and for those just trying to find where I have written down the, here, Ka. Okay, so if I pull these together, for CD, okay, Ai transpose is going to be equal to 1 by 4, 0, 1, and here we have 3Ei upon 16, 0, 3Ei upon 4, and if I do that, you will see that this becomes essentially 3Ei by 64, 0, 3Ei by 16, then we have 0, 0, 0, and then we have 3Ei upon 16, 0, 3EI upon 4. This is the contribution of CD to the structure stiffness matrix. Okay. Similarly, we can find out for BD, and this becomes then AI transpose becomes minus 1 over root 2, 0, 0, and here we have minus EA upon 8, 0, 0, and if you look at this, this essentially becomes EA over 8 root 2, 0, 0, and everything else 0. Why do you think that is? That is the contribution of BD to the stiffness matrix. Because if you look at it, what does this mean? That it only provides a rigidity towards R1. That's true, because when you have R2 and R3, okay, the bracing the member does not deform and does not provide any. In fact, the bracing member is only provided to provide an additional rigidity to the lateral displacement. That is the whole purpose of the bracing member. It is not there to take vertical loads. It's to provide, when there's lateral displacement, it's to provide, and therefore it is not surprising that it adds to this. Okay. Now the point is, I am not going to go into, okay, so we've done for CD and BD. Can we do it for A, B and BC? So AB it's going to be equal to AI transpose into KI AI. AI transpose for AB is going to be equal to 1/4, 1/4, 0, 1, 0, 0. That's just AI transpose, and then KI was equal to EI upon 2, 3 by 4, 3 by 4, 1, 2, 0, 0. So if we multiply those, we get the following. That this implies contribution of AB to the stiffness matrix is equal to, if you look at the first one, it's going to be 3 by 16 plus 3 by 16, that's going to be 3 by 8, so this is going to be 3EI by 16. The first one. The second one, this way, is going to be 0 and 1 by 3, so this is going to be 3EI by 8. This one 0, so this is going to be 0. Now we do the second one. This is going to be 1 by 4 plus 2 by 4, 3 by 4, so 3 by 8. So it's going to be 3EI by 8. Okay. Next one, 0 into 1, 1 into 2. So this is going to be EI. The next one is going to be 0, 0. So this is going to be 0. Then let's look at the third one. This is going to be 0, 0, and 0. In other words, AB does not contribute to the stiffness corresponding to R3. That's not surprising. There is no displacement in AB due to theta R3. So therefore, it will not contribute. Whenever there is no deformation in a member due to a particular degree of freedom, it does not contribute to that degree of freedom. Okay. So we are now done with AB. So we move on to BC. BC, AI transpose is nothing but 0, 0, 1, 0, and 0, 1. And over here we have EI by 2 into 0, 0, 2, 1, 1, 2. And let us see what that happens. This first one is 0 into 0, so it's 0, 0 into 0 is 0, 0 into the first one is 0. Second one, this is 0. This one is 2, so this is EI. Third, if you look at it, is 1, so this is EI over 2. Then third one, this is 0. Third one, this is EI by 2. And the fourth one, this is 2, so this is EI. So we have got KBC. And if we add up all the 4, let me put up all the 4 here and add it up. What we get, since all the EIs are the same, my stiffness matrix, my K is going to be equal to 12 over 16, so this is going to be 15 EI upon 64 plus EA by 8 root 2. Okay, the second one, if we look at it, is going to be 3 EI upon 8. The third one is going to be 3 EI upon 16. Then we again look through this, we get 3 EI upon 8. We look through this, we get 3 EI upon 16. And if we look at the third one, we get EI and 0. So we have 2 EI, and we have EI by 2, 0, 0. So this is EI by 2. Here EI by 2, 0, 0. So it's going to be EI by 2. And the last one is going to be EI plus 3 EI by 4. So that's going to be 7 EI by 4. This is my K. Okay. And my R, I'm just repeating it, is going to be 50, 0, 0. And my summation AI transpose SI0 is going to be 0, 50 minus 50. So if we look at the final solution, what we get over here is going to be equal to 50, 0, 0 is equal to 15 EI by 64 plus EA by 8 root 2, 3 EI upon 8, 3 EI upon 16, 3 EI upon 8, 2 EI, EI upon 2, 3 EI upon 16, EI upon 2, 7 EI upon 4 into R1, R2, R3 plus 0, 50 minus 50. So ultimately from this we can solve for R1, R2, R3. I'm not going to solve this because you essentially, if you look at it, you will see that in this particular case, it's a 3 by 3. You can plug in the values of EA, EI and EA. Let's look at it very slightly carefully. What is the value of EI? The value of EI is going to be equal to 1 up into 10 to the power of 5, and the value of EA is equal to 1 10 to the power of 8. And so if you look at this particular value, do you notice something? You will see that the stiffness, this stiffness value that you get, is essentially overpowered by the value of the bracing. Okay? And in fact, that is the whole point. The point why the bracing is provided is to provide lateral stiffness, and that's where it is provided stiffness, because R1 corresponds to the lateral motion of the structure. Okay? So in essence, okay, once you have found out R1 and R2, then you can always go back and find out and show you what those would be. How would I find out my SI0? My SI0 would be this. Since I know R and I have Ka for all the members, I can find out SI. Okay? And for the bracing member, the SI that will come in will only be the axial force. Okay? So, in other words, the point that I tried to make today was that it does not matter whether a member is flexural deformations, whether it has axial deformations, or whether it has a combination of flexural and axial, because all that happens is the S, V and the K for the member is different for each case, but it doesn't matter. All we have to do is, so just putting down the steps, the first step is, given the member, okay, a priori we have to know whether the member is flexural, whether it is axial, or whether it is flexural plus axial. And that always is, if I have a frame member where you neglect axial deformations, then it is a flexural member. If it is a truss member, in other words pinned at both ends, then it's only axial member. And if we have a frame member where we do not neglect axial deformations, then it's a flexural plus axial. And once you have that, okay, then all you know is, once you have this, you define your V, you define your S, and you define your Ki. And once you have this, you see the next step, Vi is equal to AIR. In this, the kinematic relationship, this is the kinematic relationship. This kinematic relationship, once you know what this is, you can always find out what this is by giving each displacement corresponding to each degree of freedom. And then, you see, the third step becomes that, look, SI is equal to Ki AIR plus SI0. So, this I know, this I know, this I know, this I can find out. Okay? So, in essence, the point that I am trying to make here is that in the stiffness method, the only difference it makes, whether you have a truss member, whether you have a frame member where you neglect axial deformation, or you have a frame member where you do not neglect axial deformation, all that does is it only affects this. Nothing else. Everything else comes out automatically. Okay? So therefore, the beauty of the stiffness method lies in the fact that it does not really matter what kind of member you're dealing with. All you need to know is, when you give R, each individual R equal to 1, you have to find out the AI, which gives the member degrees of freedom in terms of the displacement degrees of freedom. Okay? So, I am going to stop here today. And I have introduced to you the concept that axial deformations is included, not included, doesn't matter. We are going to continue looking at more problems, and each time, each example that I look at, I will highlight one important aspect of the application of the stiffness method. In general, the stiffness method is easy. What I'm going to do is specific cases. Next time I'm going to be introducing you to rigid members. Suppose I have a member which is both flexurally and actually rigid. What happens then? How do we consider that effect? Then we are going to look at, we've only looked at member effects where SI0 depend only on loads. What happens when temperature becomes an issue? You have temperature effects. How do we include those? Those are all the things that I'm going to look at in the next few lectures, and hopefully these will illustrate how the stiffness method, which is essentially the matrix displacement method, how that is utilized to analyze structures. Thank you very much.